So let's look at some examples from 9.1 and 9.2 real quickly. We're going to start by looking at using the substitution method to solve system of equations. And remember, with substitution method, you isolate a variable first. So we're going to pick one letter in one of the two equations and get that letter by itself. So looking at it, it looks like the x in the first equation might be the easiest one to get by itself. That's not the only choice, but usually we want to pick a variable where the coefficient is 1. If you think about trying to get this x by itself, then eventually you're going to have to divide by 5, and that's probably going to leave you with fractions. Same thing with getting this y by itself. Eventually you're going to have to divide by 3's, and that's going to give you a fraction. If we can keep from having fractions when we do substitution, that would be preferable. We could get this y by itself fairly easily, but if we take that top equation, x minus y equals 5, if we simply add y to both sides, then we have x by itself. X equals 5 plus y, or y plus 5. Once we isolate a variable, then remember this equal sign means these two things are equivalent. So in the other equation, we're going to replace x with an equivalent statement. So instead of calling this 5 times x, we're going to call it 5 times y plus 5. And then we're going to copy the rest of it down. So by doing that, now our equation only has y's in it. So we can get rid of the parentheses by distributing 5 times y, 5 times 5, bring down the 3y. So if we combine like terms, we have a 5y and 3 more y's, so that makes 8 y's, and we have a plus 25. If we subtract 25 from both sides, then our y term will be by itself. So 8y will equal negative 8. So if we were to get y by itself, of course, divide both sides by 8, and we get that y is negative 1. Now, are we done yet? Well, no. Our problem is a system of equations, and each equation has an x and a y. A solution to even one of these equations is an ordered pair. We just found the y value. Now we need to find what x value goes with it. So we take the y value and we plug it back into any of our equations that have an x and a y. This one is going to be the best place here because notice we're looking for x and this equation has x by itself. So all we have to do is replace y with negative 1 and we can combine those like terms to find x. So minus 1 plus 5, now we know what x is. And we didn't have to rearrange our equations again or anything. So that's our solution. That's an ordered pair that works for the top equation, and it also works for the bottom equation. 4 minus a negative 1 is 5. If we do 5 times 4, we get 20. If we do 3 times negative 1, we get minus 3. That equals 17. So yes, that ordered pair works for both equations, so it is indeed a solution. So that's substitution. That's an example of that. And the other method we do is elimination. Now, this is the problem we just finished doing, but let's look at how could we do this same problem doing elimination. Now, I often refer to this instead of elimination, I call it the addition method, because what we're doing is we're adding our two equations together in an attempt to get rid of one of our variables. But notice right now, if we were just to add our equations together, if we add this column together, we would have 1x plus 5x minus y plus 3y, and none of our variables cancel out there. But we can do something to at least one of the equations to make it so that our x's or our y's do cancel. Notice we have a positive 3y here. If we were to have a negative 3y there, when we add that column, those would cancel. Well, we can't just put a 3 there. but we can multiply every term by 3. We can multiply that entire equation by 3, and that'll give us 3x minus 3y equals 15. So now if we add our equations together, when we add the left sides together, we have 3x plus 5x minus 3y plus 3y cancels. And on the other side, we have 15 plus 17, which is 32. Now to get x by itself, divide both sides by 8, and we have x, which is the same x value we got doing it the other way, because of course the solution is going to be the same solution. So our objective here was to make our y's opposites of each other or our x's opposites of each other. Once we made our y's opposites, when we added our equations, those canceled. So that gave us an equation that only had one variable. That's something we can solve. Now we won't completely finish this problem out because we just did that problem before and saw that our x value is 4 and our y is -1. Once we get one of the values, we just plug it into either equation and solve for the other one. So let's do another example of that. So let's do the addition method again. As it is right now, if we add our equations together, our x's don't cancel, our y's don't cancel, so that wouldn't do us any good. And one thing that is trickier about this one is there's not an integer we could multiply this by to make it these opposites, and there's not an integer we could multiply this by to make these opposites. So when that's the case, or when it's not obvious what to multiply by, one, I guess you may call it a trick, or one technique we can use is to swap the coefficients. And what do I mean by that? If we want to make the x's go away, we would take this coefficient and bring it down here, and this coefficient and bring it up here. And notice when we distribute the 5, we're going to get 10x here, and when we distribute the 2, we're going to get 10x here. So those give us the same. We actually want opposites instead of the same, so we just need to pick one of them to be negative. Doesn't matter which one. I'm just going to pick that top one. So now let's distribute. So on top, -5 times 2 is a minus 10x. Minus 5 times 4 is a minus 20y. And on the other side, minus times minus is a positive 50. When we distribute on bottom, 2 times 5 is 10. Notice these are opposites. That's why we picked one of these to be negative, so that when we distributed, one came out to be negative, one came out to be positive. Sometimes both of the numbers out front will be positive because the signs are already opposite. We just have to find out what the numbers are. But when we get through distributing, we want one of these to be positive, one negative. So when we finish distributing down here, 2 times -9y is -18y. 2 times 51 is 102. So when we add our columns, the x's cancel, same signs, so we add those. Same signs, so we add these. And then to get y, we divide both sides by -38. So the 38's cancel. Positive divided by negative is negative, and we could use our calculator for that if we needed to. 152 divided by -38 is -4. So that's the y value in our solution. Now we just need the x. So we can pick either one of these equations or either one of these equations and substitute this in for y and find x. So I'm just going to take the very first equation, 2x plus 4 times y equals -10, and in place of the y, put in a -4. So we have 2x, 4 times -4 is -16. Add 16 to both sides. Those cancel, so we have 2x equals 6. Divide both sides by 2, and we get x equals 3. So our solution is 3, negative 4. And if we were to substitute that in each equation, then we would get a true statement. So that turns out that that is our solution for this one. All right, let's take a look at this one. This one has 3 variables and 3 equations. So our solution is going to be an x, y, and z, so it's going to be an ordered triple. So just a quick overview. If we start out with 3 equations and 3 variables, if we make one variable go away, then we have 2 variables. But if we have 2 variables, then we need 2 equations that have those same 2 variables. So that means we're going to have to eliminate a variable, the same variable, possibly twice. So eliminate one variable so that we only have 2 variables, but we have to do that so that we have 2 equations and the same 2 variables. And then whether we're doing substitution or addition, then once we have 2 equations and the same 2 variables, that's what we did in the first couple of problems. Then we eliminate a variable by either technique, and that'll give us one equation with one variable, and that's something that we know how to solve. We just get that variable by itself. Once we solve that equation, then we take our answer and we back substitute in order to get the other variable in this step, and then we take both answers and plug them in one of the top equations, because now we have 2 different letters. If we know 2 of these, we can find the third one. So let's just work through what that's going to look like. Let's just slide this over. So for reference, let's call this equations 1, 2, and 3. So I notice that if I add the first equation and the third equation together, my z's are going to cancel. So if we take x plus y plus z equals 5, and x plus y minus z equals 3, then when I add these equations, the z's cancel, and we have 2x plus 2y equals 8. 2 variables in this equation. We need another equation that has those same 2 letters. So we could pick another set of equations. Let's take the first 2 equations and eliminate z. Let's take equation 1. So I'm just going to, this was 1 and 3. Let's take equation 1 and 2 this time to eliminate z. So x plus y plus z is 5. 2x minus y plus z is 0. Now if we just add them together right now, we cancel the y's. But we don't want to end up with x and z. We want to end up with x and y because we need 2 equations that have the same 2 variables. So to make these cancel, they're the same right now. We need them to be opposite. So we can just pick one of these and multiply it times a negative. So the top equation we're going to keep, x plus y plus z equals 5. The bottom equation, if we distribute a negative 1, then we're going to have negative 1 times 2, so minus 2x. Negative times negative is positive y minus z. Negative times 0 is 0. So now notice our z's cancel. Z minus z cancels. 1 minus 2 is minus 1x. y plus y is 2y, and then we get 5 on the other side. So that gives us another equation that has x and y. So let's bring our first one down. Our first one down was 2x plus 2y equals 8. So now that we have two equations with the same two variables, this is a problem like we had before. So we just need to either do substitution or addition to make one of these variables go away. I noticed that if I change the sign of one of these would be opposites. So I'm just going to multiply the top equation by -1. So if I multiply the top equation by -1, negative times negative is positive, 1x, negative times positive is negative, and on the other side, negative times positive is negative. And we're just going to bring down the second equation because now the y's are opposite. So if we add these equations together, the y's cancel. 1x plus 2x is 3x. 8 minus 5 is 3. So if we divide both sides by 3, we get that x is 1. Now, we're not finished, but that gives us an x value. Once we get one of our values, we just go and back substitute until we can get our other ones. So let's take this x value, plug it into an equation that has x and one other letter. So let's look at this bottom one down here. We could have used any of these, but let's plug an x in here. So we know x is going to be 1 at our intersection. So if we plug a 1 in, we get 2 plus 2y equals 8. So 2, subtract 2 from both sides. So 2y is 6. And if we divide both sides by 2, we get that y is 3. All right, so we found x and y, so now we need to find z. So pick an equation that has z and plug in x and y. I'm going to just use this top one. This top equation, in place of x, we put a 1. In place of y, we put a 3. And we're looking for z. 1 plus 3 is 4. So if we subtract 4 from both sides, we get that z is 1. So if we just review what we did, we went from 3 equations that had 3 variables to, once we eliminated a variable, we had 2 variables, but we needed 2 equations with the same 2 variables. So we eliminated a variable using one pair of equations, and we eliminated a variable using another pair of equations. But we had to make sure we were eliminating the same variable both times. So that gave us 2 equations with the same 2 variables. Once we got to that part, this was like the previous problem. We remove one of these variables. Doesn't matter which variable. So once we remove a variable, we can solve for the other one. Once we get one of those variables, we back substitute to get the other ones. Now let's do one last one. And this one is a little bit different, but our process in general is the same. We have 3 equations, and we have a total of 3 variables. So our solution is going to be an ordered triple. Even though no equation has all 3 variables in it, our system does have 3 variables. So we want to find out exactly which values for x, y, and z will work for all 3 equations at the same time. So what we're going to do is we still need to get down to 2 equations with 2 variables. So we just need to pick which variable we want to eliminate. So if you want to have equations of x and y, we can eliminate z. Notice we already have one equation of x and y. So if we're going to eliminate z, then we're going to have to use the top and the second equation because those are the only ones that have z in them. So if we list those, oops. If this is 2, we would need a minus 2 for these to cancel each other out. So let's double this equation. So 2 times y, 2 times minus z, 2 times 3. So now notice when we add these equations together, our z's cancel, and we get that bottom equation, which means that for this particular system, we essentially have more than one solution. We have multiple solutions. So I just made this problem up. This is not, I didn't intend for this to happen on this particular problem. So let's just, to make, well, I better not do that. I was going to say, let me just rewrite the problem. Let me just give us another problem that's similar to this and go from there. But this is a technique. Normally, when we do this, these end up with two different equations, not the same equations, but different equations that have the same two variables. And then we would proceed to solving that system of equations to get x and y. And then we would go back in and plug in to get z. But let's do another one. So let's try this one. So we have 3 equations and a total of 3 variables. So we want to find an ordered triple that works for all 3 equations. So we just pick which variables we want in our system that has 2 variables and 2 equations. So if you want x and y's, then what we need to do is to get rid of z's. So this is an equation that has x's and y's in it. So we need to take equation 2 and equation 3 and get rid of z. So let's just do the opposite of that one. So let's multiply the middle equation by -1. So that'll give us minus y minus z equals -4. And we'll keep the top equation, the bottom equation, so x plus z equals 7. And when we do that, our z's are going to cancel, and we end up with x minus y equals 3. So that's another equation of x and y. So the good thing about this one is we don't have to eliminate z 2 different times to get 2 equations and 2 variables. We were given one of them, and we eliminated z 1 time to get another one. So I'm just going to copy my other equation down here. And now we just use substitution or addition to solve this one. If we add these equations together, we get 2x, our y's cancel, and we get 8 on the other side. If we divide both sides by 2, we get x equals 4. So that's the x coordinate of our solution. Now we can just back substitute that x value into really any of our equations to get our other values. If we back substitute it into the first one, 4 plus what makes 5? 4 plus 1. So that gives us y. If we plug in a 4 in for x here, 4 plus what makes 7? Well, 3. So now we have all 3 variables. Notice that y plus z, 1 plus 3 is 4 as well. So yes, that ordered triple works for all 3 equations. But this one, the way it was structured, was really shorter. It's just set up slightly in a different way. If you keep the flow chart in mind, if we have 3 equations with 3 variables, we need to get it down to 2 equations with the same 2 variables. Well, we have to know which variables do we want. we decided we wanted x and y. So we had one with x and y already, and then we eliminated z to get another one of x and y. And then once we have that, we can eliminate to get down to one equation in one variable. All right, so hopefully this will give us a good start on how to work through those homework problems.